When we add features to a dataset, we expand the geometric space our algorithms must search. Multiply those dimensions into the hundreds or thousands, and standard machine learning models fail to process the density. This creates what practitioners call the Curse of Dimensionality. It results in 3 distinct failures: computational inefficiency, poor generalization, and a lack of interpretability. Looking at the left and center panels, the math becomes the bottleneck. An algorithm that efficiently calculates a boundary in 2 dimensions requires exponentially more memory as it expands into a 3D volume, eventually becoming computationally intractable. Beyond the math, human intuition is also limited. As seen in the rightmost panel, we cannot visualize or extract meaningful patterns from a network graph representing thousands of intersecting dimensions. To manage this, we must compress the space. Dimensionality reduction requires a choice between 3 distinct mathematical philosophies to preserve the data's essential structure. These approaches are categorized into 3 paradigms: a data-driven search for an optimal view, a data-oblivious use of randomness, and a structure-driven method for signal compression. Every method involves a decision about which mathematical properties of the dataset are prioritized and which are sacrificed to keep the remaining data computable. Principal Component Analysis, or PCA, is a data-driven philosophy. It actively analyzes the specific input data to find the single most informative perspective available. Imagine casting a shadow of this wireframe horse onto a flat plane. PCA calculates the specific angle of light that creates the sharpest possible shadow, the linear projection that retains the most variance from the original object. Mathematically, PCA seeks a low-dimensional projection that minimizes the average square distance between the original vectors and their reconstructions. This is solved by extracting the eigenvectors corresponding to the largest eigenvalues of the data. This requires first calculating the data's covariance matrix, shown here as matrix A, which is the product of the data matrix X and its transpose. The Eckart-Young theorem provides the theoretical foundation for this approach. It guarantees that this specific subspace choice minimizes reconstruction error in a least squares sense. In the flowchart on the left, step 3 involves finding the top eigenvectors. This entire process is dependent on the specific geometric arrangement of the input matrix X. This dependency creates a computational limit. Extracting eigenvectors requires singular value decomposition, which becomes difficult to calculate as the number of initial dimensions increases. While PCA is the standard for accuracy, its reliance on data-driven covariance calculations makes it an efficiency liability when the dimensions scale into the millions. An alternative approach involves skipping the data analysis entirely, as represented by the question mark on this slide. We can achieve dimensionality reduction without looking at the internal structure of the input. Instead of searching for the perfect angle, we project the data onto a completely random subspace that is independent of the dataset. This works like a scrambled lens. While the absolute coordinates of the data points change, the relative distances between those points are maintained in the new space. This is possible because of the Johnson-Lindenstrauss lemma. It proves there is a linear map, W, that keeps the ratio of projected distances to original distances very close to 1. The formula for the target dimension, n, depends only on the number of points, m, and the desired precision, epsilon. Note that the original dimension, d, is not part of the requirement. The size of the starting space does not dictate the size of the final representation. Because we skip the covariance analysis, this method uses simple matrix multiplication. As the stopwatch icon suggests, it is significantly faster than PCA for large datasets. By utilizing randomness, we bypass the computational bottleneck of high dimensions. This allows for fast compression of streaming data where speed is the primary requirement. Is it necessary to measure every part of a signal if most of those components are eventually discarded during compression? Compressed sensing addresses this by looking for signals that are sparse. As shown in this 3D cube, a sparse signal is one where most components are 0, or can be represented such that only a few coefficients are non-zero. To preserve these signals, we use a projection matrix that satisfies the restricted isometry property, or RIP. This condition ensures the matrix preserves the length of the sparse vectors. If the RIP condition is met, it enables lossless compression. We can perfectly recover the original signal from a limited number of measurements. The challenge is the reconstruction. Finding the sparsest signal via L0 minimization, shown here under possibility 1, requires an exhaustive search of all combinations, which is an NP-hard problem. This search space is like a jagged mountain range. A standard algorithm attempting to find the lowest point will likely get trapped in a local minimum long before it finds the true global solution. However, if the RIP condition holds, we can use L1 minimization instead. This transforms the task into a convex optimization problem, which can be solved in polynomial time. The jagged terrain is replaced by a smooth, inverted cone. Any starting point now leads directly to the unique global minimum at the bottom. By leveraging the signal's inherent sparsity, compressed sensing combines acquisition and compression, turning a combinatorial search into an efficient linear program. Every dimensionality reduction method involves a direct trade-off between your preservation goals and your computational limits. This table compares the approaches. PCA preserves variance, random projections preserve distance, and compressed sensing preserves sparsity. The cost differences are significant. PCA is expensive. Random projections are inexpensive. Compressed sensing is cheap to measure, but requires significant computation for reconstruction. To choose a strategy, answer 3 questions. First, what is the data's nature? Is it structured or sparse? Second, what property must be preserved? Variance, distance, or the exact signal? Finally, what is the computational budget? Is data-driven analysis or speed the priority? Effectively managing high-dimensional data requires moving beyond a single algorithm and understanding the different philosophies that define data structure.